Have you ever stopped and thought about this? How is it possible that a machine weighing over 500,000 kilograms doesn't just lift off the ground but calmly flies across oceans for hours? Today, I'm breaking down how airplanes actually stay in the air, and I promise, after this video, you'll never look at a takeoff the same way again. To understand the scale, think about the Airbus A380, the largest passenger aircraft ever built. Its maximum takeoff weight is around 575 metric tons. That's roughly the weight of a fully loaded freight train. And this thing doesn't just hop into the air. It climbs to 35,000 to 40,000 feet and cruises at around 900 kilometers per hour for 10, 12, sometimes 15 hours straight. By common sense, something that heavy should be glued to the ground. But physics says otherwise. First, let me clear up the biggest misconception. You've probably heard the common explanation. Air traveling over the top of the wing has a longer path, so it must move faster, creating lower pressure, and that's lift. That explanation is incomplete and partially wrong. Real lift is more interesting than that simplified story. So how does all that metal actually stay in the air? The answer lies in four fundamental forces. Every airplane in flight is governed by them. 1. Weight, gravity pulling it downward. 2. Lift, generated by the wings acting upward. 3. Thrust, produced by the engines pushing it forward. 4. Drag, air resistance slowing it down. Think of it like a dynamic balance. When lift equals weight, the airplane maintains altitude. When thrust equals drag, it maintains constant speed. The moment there's an imbalance, acceleration happens. If net force points upward, the aircraft climbs. If it points forward, it accelerates. There's no magic involved, just forces in balance. But that leads to the real question. Where does lift actually come from? A wing has a specific airfoil shape, curved on top, flatter underneath. During flight, the wing is angled slightly relative to the oncoming airflow. This is called the angle of attack. As air flows around the wing, two things happen simultaneously. First, the airflow over the top accelerates. Pressure above the wing decreases. Pressure below remains higher. That pressure difference produces an upward force. But that's only part of the story. The wing doesn't just create lower pressure, it also deflects air downward. And according to Newton's third law, if the wing pushes air downward, the air pushes the wing upward with equal and opposite force. Bernoulli and Newton aren't competing explanations. They describe the same physical process from two perspectives. Lift is the result of both pressure differences and the downward deflection of airflow. That's what keeps hundreds of tons suspended in the sky. One of the key factors determining how much lift a wing produces is the angle of attack. When a pilot pulls back on the control column during takeoff, the nose rises and the angle of attack increases. Air over the top surface accelerates more. Pressure drops further. The airflow is deflected downward more strongly. As a result, lift increases. But there's a limit. Lift doesn't increase forever. Beyond a certain angle, the airflow over the upper surface can no longer stay attached. It separates. Pressure distribution collapses, and lift drops sharply. That's what we call a stall. And this is where speed becomes critical. Lift is described by an equation. You don't need to memorize the formula, but one thing matters. Velocity is squared. That means if speed doubles, lift increases 4 times. If speed is cut in half, lift drops to 1/4. We're talking about airspeed, speed relative to the surrounding air. The faster the airplane moves, the more air mass flows around the wing each second. The more air it can redirect downward, the more lift it produces. That's why an airplane can't just jump off the runway. Before takeoff, it must accelerate until lift equals weight. At that exact moment, the airplane lifts off. Not because it became lighter than air, but because aerodynamic forces reached equilibrium. Now let's look at the same process from another angle, momentum. A wing creates a pressure distribution that causes the airflow behind it to tilt downward. This is called downwash. Every second, an enormous mass of air flows around the wing. Aerodynamic forces change the direction of that flow, giving it a downward component of velocity. According to Newton's third law, if the wing gives the air downward momentum, the air gives the wing equal upward momentum. Lift is essentially the rate of change of momentum of the air. The airplane isn't sitting in the sky. It's continuously interacting with airflow, redirecting it. But what happens when the aircraft needs to fly slowly, like during takeoff or landing? That's where wing high-lift devices come into play. If you look out the window before takeoff, you'll see the wing changing shape. Flaps extend from the rear, slats extend from the front, creating a slot. Aerodynamically, this does 3 main things. 1. Slightly increases the effective wing area. 2. Significantly increases camber, the curvature of the airfoil. 3. Dramatically increases the lift coefficient. The increase in lift coefficient is the most important factor. It allows the wing to generate much more lift at lower speeds. Slats serve another crucial purpose. The slot allows higher energy air from below to flow over the upper surface, helping the airflow remain attached at higher angles of attack. This delays stall. That's why aircraft can safely operate at much lower speeds during takeoff and landing. Without flaps and slats, the required speeds would be dangerously high and runways would need to be much longer. So why do commercial jets cruise at 35,000 to 40,000 feet? At those altitudes, the air is much thinner. Drag is lower. Fuel efficiency improves. Drag depends directly on air density. The denser the air, the more resistance the aircraft experiences. By climbing higher, the airplane reduces drag and burns less fuel per mile. There are additional benefits. Cold air improves engine efficiency. There are fewer weather systems and storm cells, less turbulence caused by terrain. As fuel is burned, the airplane becomes lighter. That allows it to gradually climb even higher during flight, a procedure known as step climb. Now let's talk about how takeoff actually happens. Takeoff isn't just full throttle and go. It's a carefully calculated sequence of speeds and actions. Before the aircraft even lines up on the runway, pilots calculate several key speeds. V1, the decision speed. After passing V1, the takeoff must continue even if an engine fails, because stopping within the remaining runway may no longer be possible. VR, rotation speed. At this point, the pilot gently pulls back, increasing the angle of attack. The nose rises, lift builds rapidly. Then comes V2, the minimum safe climb speed with one engine inoperative. During the takeoff roll, part of the airplane's weight is still supported by the landing gear, but as speed increases, lift increases. At a certain moment, lift equals weight. The normal force from the runway drops to zero. The airplane doesn't jump. It simply no longer needs the ground. That's liftoff. After climbing out, the aircraft transitions to cruise altitude. This is the most efficient phase of flight. In cruise, lift equals weight, thrust equals drag. There is no acceleration. This is dynamic equilibrium. Now let's talk about descent and landing. Descent is not falling. Pilots reduce thrust and manage the aircraft's energy. Lift remains present but becomes slightly less than weight, allowing controlled descent. Before landing, flaps are extended. The lift coefficient increases. Minimum safe airspeed decreases. This allows the airplane to fly safely at lower speeds. Just before touchdown, pilots perform the flare, gently raising the nose. This reduces vertical speed and softens landing. After touchdown, spoilers deploy, destroying remaining lift. Thrust reversers activate. Brakes are applied. Lift rapidly decreases and the aircraft's full weight transfers onto the landing gear. Every time you watch a massive airliner lift off, it feels like it's defying gravity. But it's not breaking the laws of physics. It's using them. Lift, thrust, drag, angle of attack, everything exists in precise balance. To me, that's the real beauty of aviation. Not magic, but exact calculations and respect for the laws of nature. And now I'm curious. Have you ever wondered how airplanes actually slow down after landing? I've already made a video about that. There's another layer to understanding flight that's worth exploring. The evolution of wing design. Early aircraft had simple, flat wings. Pioneers like the Wright brothers experimented with curved surfaces after studying birds. They discovered that camber, the curvature of the wing, dramatically improved lift. Over decades, engineers refined airfoil shapes through wind tunnel testing and mathematical modeling. Modern wings are precisely sculpted. The exact curve, thickness distribution, and cross-sectional shape are optimized for specific flight regimes. There's also the concept of wing loading. This is the aircraft's weight divided by wing area. High wing loading means more weight per square meter of wing. It allows faster cruise speeds but requires higher takeoff and landing speeds. Low wing loading means slower speeds but better maneuverability and shorter runways. Fighter jets often have low wing loading for agility. Airliners have moderate wing loading optimized for efficiency at cruise speeds. Now let's consider aspect ratio, the ratio of wingspan to average wing width. Long, narrow wings, high aspect ratio, generate lift more efficiently. They produce less induced drag, the drag created as a byproduct of generating lift. That's why gliders have extremely long wings. They maximize lift while minimizing drag, allowing them to stay aloft for hours without engines. Commercial jets use moderately high aspect ratios to balance efficiency with structural constraints. Very long wings would be difficult to support structurally and would create ground clearance problems at airports. There's also wing sweep. Most commercial jets have swept wings, angled backward from the fuselage. Swept wings delay the onset of shock waves at high speeds. As an aircraft approaches the speed of sound, shock waves form over parts of the wing, dramatically increasing drag and potentially causing loss of control. Sweeping the wing backward reduces the effective airspeed perpendicular to the leading edge, delaying shock wave formation. This allows jets to cruise efficiently at speeds close to the speed of sound without encountering severe drag rise. Let's talk about winglets, those upward curving tips you see on modern aircraft. They're not just aesthetic, they reduce induced drag by disrupting wingtip vortices, swirling masses of air that form at wingtips as high-pressure air below the wing curls around to the low-pressure region above. These vortices represent wasted energy. Winglets partially block this flow, recovering some of that energy and reducing drag. The fuel savings are significant. On long-haul flights, winglets can reduce fuel consumption by 3 to 5%. Over thousands of flights per year, that translates to millions of dollars saved and reduced emissions. Finally, consider the human element. Pilots don't just push throttles and pull yokes, they understand the physics. They know how angle of attack affects lift. They monitor airspeed constantly, ensuring they stay within safe margins above stall speed and below maximum speed. They adjust power settings to maintain desired climb or descent rates. They configure flaps and slats based on the phase of flight. Every decision is informed by aerodynamic principles. So the next time you're on a flight, remember this. You're not witnessing magic. You're witnessing applied physics. Every curve of the wing, every degree of angle, every knot of airspeed, it all contributes to keeping hundreds of tons airborne. The airplane stays in the air because engineers designed it to exploit natural laws, because pilots operate it within precise parameters, and because every component works exactly as intended. And that, to me, is far more impressive than magic could ever be.